We're going to start this session now with the awesome Mohammad Haghighat, who I've actually known for quite a long time since he came to visit us at Google when he was working on Whirlpool, doing some interesting machine learning stuff there. Now, just recently at Intel. I'm sure he's going to have some really interesting insights into the core ideas of how to use deep learning for these kinds of vision problems. So I'm really looking forward to hearing what he has to say.
Thank you very much, Pete.
Take it away, Mohammad.
Thank you, Pete. Yes, thank you everyone for joining this session. I appreciate the time that you put here, and hopefully we will have an interesting session. So this is going to be a very high-level introductory session about AI, the conventional algorithms, like the classical machine learning, as well as the new deep learning. I would love to have the session to be interactive. So if you have any questions, please feel free to interrupt me in the middle. Don't be shy. Your question may be the question of a lot of people. So let's have it interactive. And whenever you don't understand anything or you want me to explain something further, please go ahead and let me know. And we can start. So this, as I mentioned, this session is going to be a very high-level introduction to AI. I will talk about the conventional algorithms and then move to deep learning. We will talk about the neural networks and how deep learning works there. We will start with the fully connected networks, which are the simplest form of neural networks. And then the elements of the neural network will be talked there, and we will talk about the neural network training very briefly, because there is going to be another session about the training. And then we will move to convolutional neural networks, which is the popular type of neural networks for computer vision. And this is a computer vision summit, so that's why we are talking about that. We will talk about the building blocks of ConvNets, and then applications of CNNs and some popular CNN architectures that are not very new, but they are the beginning, most fundamental ones. That's why they are in this call. You will have more of those and more interesting ones in the object detection session, hopefully, and you'll see those. So the first slide here is about what is machine learning and what you are expecting from a machine learning algorithm. So basically, you can think about it as, for now, you can think about it as a black box. So you are entering the data inside this black box and expect an output. And this output, the input data can be various things, and the output can be various things. When the input data comes from the visual sensors, I mean like images or videos, then it takes us to the realm of computer vision. And if it comes from other sources of information, so for example, if it's like if it's language, it's like text, it goes into the realm of NLP, it's natural language processing. So they are different ways of, different types of data input and different outputs that we are expecting from that. So the first example on the top is a classification problem. What classification does is gets an input and assigns a class to that input. So for example, you give a picture into the ML model and you ask what this picture is. And if the model is trained well, if it's a working model, it will tell you that that's a person. And then it can be like, this classifier can have many different classes. It can detect like person, dogs, cats, and it can be as granular as possible as you can do, actually, your data permits. So for example, it can be a classifier like that can detect that, oh, this is not a person, this is a dog. Or it can be a little more granular and say that, oh, not only this is a dog, this is a beagle. Or not only this is a person, this is a woman. So it can go granular like that in the classification. But basically, the whole idea is classification here. You just assign one output to this input that you had. or sometimes multiple outputs. Or the second example here is about, again, vision related, is a segmentation problem. So you give an image and you ask the model to not only tell you that this is a picture of a person, but show you where that person is in that picture. So it kind of draws a label on top of that. Maybe I shouldn't come in front of this. So, and it draws a label on top of that, that this is the area where the person is. We will talk about how those can be defined. It can be either like pixel-wise here, or it can just draw a box around it that this person is sitting here. Or another network is like the activity recognition. So it's like you give a picture into the model, and it gives you a description of that picture, what that picture is. So the input of this is an image. Output of it is a sentence, like a meaningful sentence that tells you, oh, it's a person dancing on the beach. So in all these examples, the inputs were images. So, but the outputs are different. So in the first example, the output is just a class, which is usually not like that it says it's a person. It gives you an index. So if we have 100 classes, say class number 5 is, say, person, and then it will give you 5. And you know that that 5 is the output that the word person, or the label person. The second one gets an image and gives you another image. But in that image, it's like a mask. So it's like, imagine that it's a picture that has only zeros and ones, and where the person is are ones and the rest of it are zeros. So it's basically a mask that maps on that image. The third one gives you a sentence again, as I mentioned. And these on the left-hand side are computer vision related. But machine learning, as I mentioned in the beginning, is not only computer vision. The input data can be other things. So for example, you can give a comment that was mentioned about a movie or about a product that is in the Amazon's, say, reviews, and feed that text into a model. And again, if it was a classification problem, you just want to know that, was it a positive review or was it a negative review? So you want to just understand what are if they are positive, this has the positive sentiment or negative sentiment. Or there are like these grammar or spell checkers that you probably have seen in a lot of tools, that you write something wrong and it passes through this model and says that, oh, most probably you meant beginning and that N is just have moved here, so it gives you a recommendation. That's also an ML model. Or there are other solutions as well. I don't know which company is using which algorithm, but it is also solvable by ML models. Or you can give it a speech, a signal of a speech, and then ask to transcribe it. So it's like what you see in your voicemail, for example, that it transcribes a speech. So that's also an ML model. So basically, depending on what your input is and what kind of output you are expecting, your model architecture is going to be different. We are mostly focused on the left-hand side problems here, and the inputs of our models here are either images or videos. So, okay. So if you go to the next slide, is there any questions? Okay. So this is the ML world has changed drastically in the last 10 years, I would say, since 2012. We will go why 2012, but before that, most of the machine learning and computer vision solutions were following a very different structure, the upper row here, than the one that is now. And those solutions are currently called conventional, or some people call them classical. But they are still very useful. They are still, as Jeff was mentioning in the morning, not everything is solved by deep learning. We still have a lot of conventional or classical algorithms that are very good fits for a lot of applications. So we still have those. So for example, if we wanted to do that person detection, that the first example that I showed you in the beginning, what we would do previously in the in classical sense, we would have several steps. The first step was like feature extraction. You are extracting some type of features from this image. Because the image basically for the computer is a matrix of numbers. It doesn't understand what those numbers are, but you extract features that may represent this application better, the things that you want from this application better. So this example, for example, is like a Gabor feature. Gabor feature was one of the popular feature extraction techniques. They were just HOG features, histogram of gradients, oriented gradients, or they was like the LBP features. There were so many different feature extraction techniques that researchers in the computer vision field would take them, try them, okay, which feature extraction technique works better for me in this application. And then, of course, and you could also have several different feature extraction techniques, not only limited to one. You could just get a lot of features from different feature extraction techniques and then fuse them together. That was called something called feature fusion, and then move to the next step. And the next step, as I mentioned, since we had a lot of features in this step, there was like the problem of now we have a lot of features. We don't know which one of them are really informative, which one of them are useless. So there were some methods called dimensionality reduction or feature selection, it was also called. Like PCA was one of them. There was LDA, GDA. There were so many algorithms over there that was supervised and unsupervised. Then that was used to reduce the dimensionality of those features to the features that are going to be useful for you and are going to be representative of what you are looking for in that image. And then, of course, the last step was a classifier. This is an example of a support vector machine, for example, was one of the classifiers. KNN was another one, K nearest neighborhood. So there were a lot of different classifiers as well. So when you, for example, you extracted these features, you reduce the dimensionality of those features, and then you map those features in a feature space. So imagine like it is the feature space is usually high dimensional. It's hard to show it in that two-dimensional thing, but that's just for representing it. There is usually no two features is usually good for classification problem. But imagine that the thing that we were doing in the first two steps was to extract features in a way that, for a classification problem, the features of the same class are close to each other in the feature space. So for example, if we had a classifier that was detecting persons, dogs, and cats, these three classes, so you want the features that are extracted from the images be in a certain way that all the features vectors extracted from people are gathered together and creating a cloud in the feature space here, and they are far from where the feature vectors of the dogs are collected. And then with the classifier, you understand that, oh, this is the border between person and dog. And later, when you want to actually do this in your application, in action, you take a picture, you extract the features the same way that you did while you were learning that how should I separate these two, and then do the dimensionality reduction and see where that new feature vector falls. Does it fall on this side of the border or does it fall on that side of the border? This side of the border, if it's here, it's a person. If it's on the other side, it's a dog. So that was how it used to work. And then there were all sorts of, so now you can imagine that it's very important to find the features that actually gather all those samples together, and also a classifier that knows how to draw this border. It's not usually a linear border, it's usually a very curvy border in a very high dimensional feature space, not a two-dimensional or three-dimensional. But what deep learning has done is just consolidated all those steps into one network. So basically, what we are doing is we feed the data into a neural network. We will get into what neural network is and get the output, and let the neural network figure out what features it needs to extract, what dimensionality reduction it has to do, and what kind of classification it's going to do. So instead of the researcher choosing between the feature extraction techniques, the neural network is figuring that out. And this has several benefits. One of them is that, yeah, of course, researchers cannot try all possible feature extraction techniques. We may not even don't know a lot of feature extraction techniques. Gabor is famous, HOG is famous, but there are a lot of features that these feature extraction techniques cannot even extract. But now the models here, the neural network models, are able to extract such features as well. Now the problem is the other way. Now neural networks are extracting some features that we cannot explain. So if somebody asks me, so what kind of features it extracts that it says it differentiates dog from a cat? I don't know. It extracts that. There are ways to explain it. There are ways to visualize it, but usually the features that are extracted are not explainable. But we have intuitions of how the system works and what we can do to design this neural network that it will give you the useful features. So I'll go to the next slide. So now we are talking about what neural networks are. The neural networks is basically we want to mimic how human brain works. And human brain, mind broke for a second. So human brain consists of neurons, and they are connected to each other, and the information is passing through a network. Or that's at least how we think human brain works. And usually it's like there is a synapse part that it gets the information from the previous neurons. It gets some signal, electrical signal, say, and then aggregates that and then passes it through the axon, and it goes out to different branches where there are other neurons connected to it. So for example, here, the information comes from previous neuron, and the synapses in this neuron gets that, it processes them together, aggregates them, and whatever it has, the output, it passes that through different axons, and it goes and opens, and then we have other neurons that are getting that. So we are trying to mimic and create the same thing in artificial neural network. So basically one neuron that you see up there, we replicate that here in the bottom. So what we see is that, yeah, there were series of information. So say that there are n number of input features, whatever those features are. We don't care at this moment. So they come here, and then they are multiplied by some weights, which we don't know what those weights are. And then they are aggregated, and that thing passes through a function, that number that has been summed up. It passes through a function which we call activation function, which is usually, not usually all the time, it has to be a nonlinear function. We will get to that, why it is nonlinear. And it gives you an output. And then this output is one of these for the next layer of the neural network. So when you stack them together, it looks something like this. One of these here is one of those neurons. So it is connected to all the neurons in the previous layer, and the output goes to all the neurons in the next layer. This is called the fully connected neural network, because it's like every neuron is connected to every neuron in the previous layer as well as every neuron in the next layer. So that's why it's called fully connected. You will hear that a lot in the next sessions. And it is also called dense layer. That's also another name for that. So some call it dense, some call it fully connected. And there is an input layer, of course, and there is an output layer. So I think I have an example for this. No, we will get there. So what happens here is basically each of those neurons are getting inputs. There are multiplications of each of these input data into these weights, yet we don't know what those weights are, and then summed and passed through the activation function. And then that's the output that passes through next one. And there is this universal approximation theorem that says that if you have enough neurons and a nonlinear activation function, you can approximate any continuous function with a neural network. That is a proven theorem in algebra, and it's like, and the whole idea of neural networks and solving the problems with that is based on this theorem. So if you can approximate any formula, any equation with neural networks, then you can optimize that, the same equation with the neural networks as well. So if you can approximate that, you can find the minimum of that or the maximum of that. So that's how the optimization process is where we learn these weights. So we will get to that. Imagine this is an example that I've put here. This is not how neural networks work. The inputs are not like you give me the color, give me the taste. So, but it is to simplify how it works. So say that we have a fruit classifier. It knows apples, bananas, and oranges. So it gets some information. So input data is some information that we have from this fruit, the picture of the fruit, or it can be just somebody is describing that fruit with these 4 features. And then we say that, oh, this is the color, that's the taste, this is the weight of it, and the shape is spherical, for example. And then it passes through these things. And the weights are in a way that the index that is for the orange usually gets the higher number than the others. So for example, here you can see that the last one has 0.83. Say that all of them sum into 1. It's like you can imagine that it's a probability of this fruit being one of those classes. So the probability of this fruit being orange is 83. The probability of this being banana is 5%, and being an apple is 12%. So, of course, ideally, if our neural network was working perfectly with no mistake, it would have said it's 100% orange. It's not banana, it's not an apple, I have no doubt. So that is where that difference happens. I have this, so that's the ideal output that we were hoping the neural network to give us, but it usually gives us something like this, if we are lucky. In the beginning, it doesn't even give that. But what happens is that we calculate that error that is like the difference between those, the ideal output and the output that we have got, the predicted output. We calculate the difference between those two. There are a lot of different ways of calculating that. They can be there are different error functions. You can like use a mean squared error. You can use a cross entropy error. A lot of different ways to calculate that. That's not important, at least here, for the scope of this talk. But you calculate that error. The larger that error is, you know that your model is bad. The smaller that error, you know that your model is actually good, is getting better. So what we do is basically in the training process, we get that output, and correlated to the magnitude of that error, we tweak the weights here, the weights that I talked about. So these W's here. We tweak them in a way that this error becomes smaller. So, and yes?
Are the final layer outputs always weighted, normalized, whatever, such that they sum to 1?
Not necessarily always. For classification problem, yes. For classification problem, we usually do that. It depends on what's your problem. So not your problem, sorry. So what the problem is, the application's problem. And then here, for example, there is a layer, usually the last layer, has an activation function called softmax. And what softmax does is normalizes the output layer so that one of the outputs goes to maximum, and the other ones are usually pressed down, pushed down, but the sum of them is 1. That makes it look like a probability distribution for you. And then usually in classification problems, we have that softmax layer at the end, yes. But for other problems, we have other things that I will get to them. So, yeah. So how the training process works, I'll get to that here. So I told you that we can actually create any function with neural networks. We can approximate any function with neural networks. This function has a distribution. Here I have put a very simple distribution of a function, and imagine that that's our cost function. What cost is? Based on that error that we calculate, we define a cost. So if we are going to, so for example, in the previous example, it was like we wanted to minimize that error. So the cost function is whatever minimizes that error. And then we map that cost function. We are hoping that our neural network is approximating that cost function. And what we are solving here is to find the global minimum of that function. Here, it's going to be here. If we reach here, if we find the weights, this is the weights, and if we find the weights in a way that we are here, our cost is going to be minimum, and our model, then we can call it it's fully trained. But usually we cannot solve that huge problem because you saw how many weights are here. It's like the dimension of this equation is huge, and we cannot solve that in regular mathematical ways. What we do here is like we follow a gradient descent algorithm. And what actually made it work for deep learning, because now there were even more layers and weights, it made it what we had over there is the stochastic gradient descent. That is like looking at a smaller area and try to optimize from there. And I forgot to tell you about what deep learning is. So previous neural networks only had 3 layers. The neural networks is not a new concept. We had them since 1980s. And usually it had 1 input layer, 1 hidden layer, this is called hidden layer, and 1 output layer. And the reason that it was limited to that, because we couldn't process more than that. That's this many connections is hard to solve. But then, since in the last 10 years, we had enough data as well as enough computation power. So it's like you have 2 equations, 2 unknowns. How many unknowns you have? It's in the math. You need to have that many equations to be able to solve that problem, right? So usually, if you are creating a deep neural network, the number of weights here is huge, is enormous. It's usually in the range of millions. And when it's millions, you basically need million equations. What the equation is basically the input data and the output. So equation here is, where is that orange thing? So equation here is that the input is this, is the orange, sour, say, half a pound spherical, and the output is that, 0, 0, 1. And that creates one equation. So if you multiply all these into these weights and get to equals that thing, that's one equation. But you need this many equations, theoretically, you need this many equations to solve that many unknowns, which is here. So one of the things that made deep neural networks possible was the enormous amount of data that we had recently. It's like you can now, for example, there is an ImageNet database that has 14 million images of 1,000 classes, which is a very popular database. Previously, we didn't have 14 million images. Even if we had, we couldn't process them in the computers that we had. But now it is possible, and we can solve these equations. So yeah, here, what we are doing is basically we have the cost function. We have mapped that. We have calculated it. And this is done by the gradient descent algorithm. So in every location that we get the output, we calculate the cost at that point. So in the previous example, for example, the output for orange was not 1, was 83. 0.83. So if you put those, if you calculate the error, you're going to fall somewhere in this cost function, right? So you are basically here. You are here. And now, where to go to minimize this? If you calculate the gradient of this, the gradient of this cost function at this point is this line, right? So we want to go in the direction of the gradient, but the opposite direction. So it's the negative of the direction of the gradient. And how much we want to go, that's something that you will hear as the learning rate. So you will hear this word, it's the learning rate that tells you how big of a step you need to take. If it's a small step, it takes forever to go here. If it's a huge step, it may jump from here to here, and it will never see here. So it's like, because we are eventually on the same curve, right? So this is how it works. So we calculate the gradient here, then we get the negative of that gradient, and then we pass that through the weights with a process called backpropagation, so that we can adjust the weights in a way that that cost goes down a little bit. And that's one iteration in the training process. Yes?
How do you get the gradient if you don't know the cost function? In multiple points, you find a difference kind of thing?
We know the cost function. Cost function is something, no, sorry, we don't know the cost function, we know the cost, which is the output. And the cost function is the neural network itself. So that is like, in every layer, we are calculating only the cost for that layer and backpropagate. So how it does is, let me go back here. So imagine that we have this output. So I will simplify it significantly here. So just suppose all the values are positive. These are just assumptions. This is not true, but I just wanted to make it simple. Just suppose all the values are positive and all the weights are positive. What you want to have here, you see that this is the result, and this is the ideal output that I should have had. Now you know that this value should have been higher, those values should have been smaller, right? So one thing that you can say here, that the only thing that you are changing here are the weights. So I know that these three that reach to this output, maybe their weights should have been a little bit higher, right? And the weights that are for these three should be a little bit lower, because we don't want this to be 5, we want it to be 0, right? So we know for this layer, right? So we can adjust these weights. And then we backpropagate. Now, here, what we are expecting here, based on the error, the ideal output of this layer compared to the predicted output of this layer. If we compare those, the same thing is that we know that which of those should be higher or lower according to the weights that we had. It's connected to the next layer, and then we do the same thing for this layer, and so on. We go back. This is the backpropagation we do for every layer, and then calculate the cost for the next layer and the gradient of that cost for this layer and go back. So this is not one cost for the whole network. This is the cost for the final layer, and then it goes back. Did that answer your question? There is going to be also a session in training that I hope that will talk in more details. I'm trying to here not to have any formulas so that it's simple. Yeah. So that's how the training is working. Yes?
Is there any chance to settle with local minima instead of global minima?
Yes, definitely. Yeah, it is. That's actually one of the problems that we have. It usually gets stuck in local minimas, and we are not able to find the global minima. But there are also some ways. What we do, for example, it's the initial weights are usually random. It's like with the random weights we start. And there are a lot of different randomization techniques that are trying to solve this problem. That's one of the ways. And there are also some ways to generalize, because usually what happens in local minima is that your algorithm is fixated into the the samples that you have used for training. It cannot generalize. So the ways, the methods that are used for generalization also help to not get stuck in local minima. Yes? Okay. So, yeah. Now we go to the computer vision problem. What computer sees in an image is not the image. Our brain is so good, we look at this and say, oh, that's a face. Not only it's a face, it might be a Lincoln. So it is like that's how our brain works. Our brain is fully trained to detect persons, and it's really good. But what computer sees is the value of each of these pixels. So basically, it sees this, a matrix. And how we can interpret this matrix to a face. And it's really hard. And what we were doing, for example, in conventional computer vision algorithms, we were extracting some features. So those features, for example, a face detection algorithm that is very famous, it's Haar cascade. And those are looking for dark and bright areas that are near each other. So for example, if there is a dark, bright, and dark, like close to each other, that's probably where the eyes are. Or if there is a dark contour around it, it might be the contour of the face. So all those things you aggregate and then find where the face is. It was pretty successful algorithm. It's still used in a lot of applications, Haar cascade. That's what OpenCV has. But that's not how neural networks work. So imagine that a very simple pattern in this matrix, excuse me, is an edge. What is an edge? Is where we have neighboring pixels that some of them are significantly higher than the others. So you can see there that there are zeros on the upper left corner of that box, and then there are 255s. So just to let you know, it's like each pixel is represented by 8 bits. So it's basically from 0 to 255 in computer vision. And 255 is white, and zeros are black. So it's a gray level between black and white. And color images are basically following the same thing. But there are 3 gray level layers for red, blue, and green. And we have different values for each of these that represent a color. And yes?
Does that also apply if you have like more than just RGB? If you have a special camera which may have like 16 bands?
Yes, it can be more than 8. Yeah, it's possible. Yeah, it is. This is like the common way. It's usually 8 pixels, but it can be more pixels, of course. And it's not always even RGB. There are different also channels, types that you can have your data. It's YCRCB, or there are different ways. So yeah, here is like the simplest, I would say, a simplest pattern that you can extract from this image. It's an edge, and that edge is the place where higher pixel values are neighboring lower pixel values. So in the previous example, what we saw was that in the orange, in the fruit detector example, if we change the order of the taste or shape or the color, it wouldn't matter. But here you cannot mix the pixels. The neighborhood is important. How the information are close to each other is important. You cannot mix that. And we have to have a network that understands this. And other than that, there is like, you can see that the neighboring pixels in a very small area are correlated with each other. For example, in a picture, you don't have, unless it's a noisy picture, you don't have a bright, very bright pixel close to a very dark pixel. Usually they are correlated, and if they are not, it's like there is a feature sitting over there. It's like that there is something that is like an edge or a corner or something. And so, but usually if you go farther from that small neighborhood, then the pixels are not correlated. So although it's very important for me to have So imagine this 3 by 3 center here, or here. There are like zeros on top and 255s here. It's important for me to keep the location of these things intact because I want to detect this edge. But when I'm there, I don't care about what's happening to the things here, right? So you are basically interested in very small region of the picture, and the location of those pixels matter. And then, yeah, that's the thing. And there is another thing here. And the location of those pixels beside each other matter. But for the classification application, where that area is doesn't matter. So it's like the cat can be in the bottom right corner of the image or in the middle of the image. It's still a cat. So I am not going to say that if you wanna learn a cat, there should be an edge here. No. If the cat moves down, the edge is not there, it's here. What is important is like, not only if you found the edge, now we want to put them together. So there is an edge here, another edge here, another edge here. And these edges have their own angles, right? This is like the edge here is vertical, then it's like 45 degrees, goes up to here, say like 75 degrees, and so on. And the combination of them together is the more important thing than where they appear in the picture. So this is what convolutional neural networks have taken into account. So what it does is says that instead of connecting all these pixels, like the fully connected layer, to an output, let's only focus in a small area. And it's like a 3 by 3 area, and extract the features from there, and move on and see that if where that feature exists in the picture. So it's like here you can see that there is a filter. Imagine that filter is on the top, is an edge detector, is a vertical edge detector. And then it passes through, sweeps the entire image and finds where that thing is. And then says that, oh, there is a vertical edge here. And then there is another filter that is a 45-degree edge detector. And then it sweeps on the image and finds that, oh, there is another, this 45-degree edge is now here, and so on. And this is what's happening in this convolution layer. This is called convolution because this is like the filter here is convolved with the underlying image. So basically what happens is like when this sits there, the values of the filter is multiplied to those values. This is actually the weights that you had in the network, right? These are multiplied by those values, then they are aggregated, then they go into an activation function, a nonlinear activation function. And this has several benefits. First of all, imagine if you were connecting every pixel of this to an output layer. You had a lot of different connections and a lot of different weights to train. Now it's like you have only 9 weights, and that is shared between all throughout the whole image. And then the previous network that was like, if you had trained the previous network that every pixel of that was connected to the next layer, then it would learn that the cat in the center, for example, has this thing, this vertical edge on this part of the image. Then if you move the cat, it wouldn't be able to recognize that. But now when it is shared, it's looking for those edges, for those little features, low-level features, and putting them together. What the next layer does, so we had this, each layer of the neural network, right? So what the next layer does is basically learning how those features now together means what. So we will get to that. Let me first talk about this convolution layer. And so basically that's the filter. I described that. It sits on the image. It multiplies to those values and creates an output for you. So we get the summation of those, and it's the output. As you can see, the output is smaller than the input because we get this here, and then we move this a little bit ahead and calculate the output here, and that's the next number, and so on. And then we reach the edge of the image, so we cannot go beyond that. One way to solve this problem is to pad the image. So we pad it with 0, so it starts from this corner, so we have the same size. Not necessarily this is a good way to do it, but for some applications, padding works. For some applications, it's not necessary. We don't need that. So it's something that is a design choice. So when you are designing a neural network, you have a lot of choices. You can have the size of the filter. Not always it's 3 by 3. It can be 5 by 5. It can be 7 by 7. Or the padding. Do you want to have padding? You don't want to have padding. So there is usually a term that is used here. It's same versus valid. This is what they call the same padding. When you hear same padding, it means that the output is the same size as the input. So if it's like a 3 by 3 convolution, then you have 1 pixel around the picture. And if it was 5 by 5, since this was going to be center of a 5 by 5, you needed 2 pixels, 2 columns and 2 rows. So that's how it is the same. Valid means no padding. So it's like it's only in the valid area of the image. It's running in the valid area of the image. And the second thing is the stride. How much do you move? Do you move 1 pixel? Do you move 2 pixels? These are also some parts of the architecture that you can design. That do you want to? Is it necessary to keep them only 1 pixel moving, or do I want to move 2 pixels and have a smaller output? And what happens in a neural network? This was just one filter, right? Imagine that in the this is like the filter. One of these filters is extracting the vertical edges. We have another filter that extracts the horizontal edges. We have another filter that extracts another different pattern. And you put them all together. You have several filters. And this is now, the image here is different than the previous images that I showed you. Those were black and white images. It's gray level. It's one channel only. Usually the pictures are like this. There is a RGB for it. It's a cube. It's not a matrix. It's a tensor. And so the filters also have a dimension of 3 on one side. So it is like this is one filter. This is another filter. They give an output. You have several of these filters stacked on top of each other. They give you outputs, and those are stacked on top of each other. And then that thing passes through an activation function. And then this activation function is nonlinear. ReLU is one of the famous ones. It's rectified linear units. So then it gives you an output over there. And one way to also reduce the size here, it's like a dimensionality reduction, is to have max pooling. It's like then we have another step that gets the maximum of each of these areas from the image. And this is very useful because it generalizes it. It doesn't matter where that edge was, for example. If it was in this area, I accept that. So it generalizes the area in the feature map and reduces, of course, the dimension so that for the next step, we are dealing with a smaller image. That's also like a kind of image. So we have passed this 3-dimensional into another dimension, and then the next layer it passes like that and goes forward. And when you put all these together, it's like one layer of networks, one layer of convolution, sorry, and then the output of the input of this is an image, and then output is the output of the number of filters that you had. So if you had, say, 50 filters applied to this image, then you would have 50 outputs here. And then with the max pooling, we are making it smaller, and then another convolutional layer, and then another max pooling. And at the end, you can also put now all those outputs together and connect it to a fully connected that we talked about, and have a classifier that is like 10 classes between 0s to 9, and have a digit classifier and a number classifier. This is actually one of the famous architectures. This is called a convnet architecture. So how those layers are, how those are defined. So for example, this is a this is like a 5 by 5 kernel. Kernel is also another word for filter that I mentioned. So it's a 5 by 5 kernel with valid padding. It creates that output. Then it's a 2 by 2 max pooling, another series of 5 by 5 kernels. This is a famous architecture called Linnet. introduced by Jan LeCun. So it was in 1998. But yeah, so here is the slide that I wanted to talk about. The first layers, as I mentioned a lot, it's like detecting the edges, right? But those are the filters that I have used, several filters. It's like some of them are detecting horizontal edges, some of them vertical, some of them in different angles. And then when you put them together in the next layer doesn't see pixels anymore, sees these, right? With the pixels, we were detecting edges. With edges, what we can detect? We can detect now corners, for example, and how wide those corners are. Say that, oh, we detected, oh, a 90-degree corner here. Then the next layer sees that there are 4 90-degree corners looking in this order, close to each other, so probably I'm looking at a square, and so on. Then when you move deeper in the neural network, the shape that you are looking for is being represented. In the earlier stages, it's like very simple patterns. But then as you move in, then you can actually find the faces. And you may also find faces of different people and be able to classify me from you or other people. So that's a face recognition problem. And so this is how it works, or at least how we think that the neural network works. When I was saying that how we don't know how the features are extracted, this is the guess that we have. And the visualizations that has happened on the neural networks in each layer have shown that, yeah, this is what it is. And there are different applications of these things. It's like a classifier that we talked about. You feed in an image into the neural network, and it gives you outputs that are like the outputs of the number of classes that you have. This is like a cat and dog classifier. And of course, the dog value is going to be high if this model is trained well. There is another application is called object detection. It not only tells you it's a dog, or it also tells you where that dog is. Here is the output is not like the probability values, but also a box. It's like, and a box can be represented by 4 values, x and y and width and height of that. It gives you an output that this is the x, y, width, height, dog. X, y, width, height, another one, cat. So it gives you an output like that, which is an object detector model. There are a lot of different architectures of these as well. Or there is like a instance segmentation. It doesn't give you a box, it gives you the mask that each pixel belongs to what object. So these are like, it goes back to the first slide that I showed you. But all of them, the internal part is the same thing, is the ConvNet. It's a convolutional neural network. And for that, there are a lot of different architectures, and that keeps evolving. One of the ones that were very famous was AlexNet. It was introduced in 2012. There is a challenging computer vision called ImageNet classification. People were working on that. ImageNet is that database that has 14 million images and 1,000 classes. They were trying to solve this problem and being able to increase the accuracy of that as much as possible. The conventional algorithms were working, and it's like every year there was 1% improvement, 2% improvement. That was like that. All of a sudden, in 2012, AlexNet came and reduced the error by 9%, which was like impressive. And after that, conventional computer vision problems for image classification became obsolete. Everyone was interested in going and following deep learning and convolutional neural networks. And this is, as you can see, it's like 5 convolutional layers followed by 3 dense layers or fully connected layers that we talked about. And so these are like, the first layer has a kernel size of 11 by 11, the next one has 5 by 5, then 3 by 3, 3 by 3, and so on. And this is completely design choice. So the designer, Alex, has chose this. He could have chosen something else. The same way that VGG came 2 years later. AlexNet reduced the error, top 5 error of ImageNet from 25% to 16%. And VGG 2 years later reduced that 16% to 7% with this new architecture. Basically, it's the same thing, all those things, but there is different set of these kernels. Here, for example, they have only used 3x3 kernels, and they have said that, okay, we will stack 3x3 kernels and then move forward with that rather than having 11x11 or 7x7. And then these are like the max pooling layers. Then at the end, it's softmax layer that I mentioned in the beginning. This is VGG 16. It has 16 layers. There's also VGG 19 that has 19 layers. And this reduced the error to 7% from 6. And that was also significantly, that was significant. But then a year later, ResNet came. And this was really a revolution. And this reduced that error to 3.6%, which was very impressive. Imagine that 3 years ago, we were at 28%. Now we are at 3. And that 28% was the result of 40 years of computer vision. And now in 3 years, we have reduced it to 3, which was very significant. And the thing that ResNet could do was to, so what happened in VGG versus AlexNet? AlexNet had 8 layers, VGG could do 19, and now they wanted to do more, but there was a problem. You couldn't train that because of the thing that you asked. It's like when we were doing backpropagation, when we were carrying the gradients, they become smaller and smaller. And when you come towards the beginning of the model, since they are so small, they vanish and they become 0. You basically cannot train the earlier layers. So that was the problem. That was solved with these things called residual blocks that ResNet brought. And they could go deeper. They went like, here in this example, it's 34 layers. But yeah, this is almost the last. So then there's just one more, I think. And then, no, 3 more. So what they did, they could actually go up to 152 layers with this and reach that sweet 3.6% error. And what it actually does, I will very briefly talk about that. So in each layer, we get an input, and we pass it through some weights, an activation layer, and so on. What they did here was that let's not calculate the weights that gets the output. That's, for example, here you have an x, and your output is f of x. But if you just add that input x after 2 layers, what this thing in the middle is calculating is the delta between x and f of x, right? So basically, it's the residual. So it needs to learn a very small thing, not much. And sometimes that residual can be 0. So previously, if it was 0, if these weights were 0, what would happen? If you backpropagate, you reach a 0, and now everything is multiplied by 0. I'm stuck there. But now, since there is that connection, even if this is 0, I still can go from there. So that made the way to backpropagate, and that was very revolutionary. After that, most of the architectures are using these residual blocks. Here is a trend of classifiers. It started with AlexNet here in the late 2012. Now it is like I got this a few days ago from Papers with Code. And now we are somewhere close to 90% with efficient nets. And then the similar thing is for object detectors. We had faster RCNN that we had average precision of 20%. Now we are in the ranges of 60s. And yeah, these are all different architectures. What we talked about today was the basic fundamental building blocks of most of these architectures. They have some little tweaks around them, but it's like the ResNet that had a connection, a skip connection, they also call it. And there are like InceptionNet has like, say, there are multiple kernels together with different sizes aggregated together, and so on. There are different things, but not, hopefully you will understand when they talk about those things. And that's it. So I am used all the time.
Awesome.
Thank you.
Thanks so much, Mohammad. I think this has been great. Maybe a round of applause.
Thank you.
And I know we've been doing questions throughout the talk, but if you have questions, we've got a few minutes left. So if you'd like to come up to the mic and ask any questions. I mean, while somebody's coming up, I mean, you've done a really good overview of kind of where we've come from and where we're at. What are you most excited about that's kind of coming down the pipe, I guess?
What I'm most excited about is that these are actually going to real applications. Previously, we didn't have those. There was, my PhD was on face recognition, and at that time it was not widely used. It was something that universities were working on. And you had to have frontal pictures, don't smile, the same way that we do, in the passport pictures. But now, it doesn't matter. I will take a picture of you from a hidden camera and I still recognize you. And that makes it applicable and feasible. And this is like a creepy application that I told you, but there are a lot of good applications for that too. It's like a lot in healthcare, for example. There are a lot of what makes the autonomous vehicles possible these days are all these things, the improvements that we have. That makes me excited.
Awesome. So yeah, if you want to jump in.
Sure. I have so what you talked about images, does that scale for video as well, or you have to take into account some kind of...
It does. And in videos, you have one more dimension. It's like not only the width and height of the image, but there is also temporal dimension, so that it's basically the images that are coming one after another. There are different types of neural networks that are called recurrent neural networks that are usually good fit for those. But they also, for each individual frame, there is the same CNN that is happening. The output of that, then it passed in that recurrent neural network to do that.
This might be a loaded question, so pick your favorite 2-minute answer if that's the case. But originally, when you showed the deep learning networks, you said all the weights are randomized to begin with, and you let it figure out everything in terms of that. With the CNNs, you're seeding it to say, hey, what I want you to do is convolution. And you gave the example of different directional edges on it. Yeah. Is the first layer of that typically seeded specifically?
No. Those are learned by network. So in the beginning, it's random. Those things that you saw, the edges, it's not like that. It's like a noise. Old TVs that had white and black, when it was noise, there was no program. It starts like that. While the model is trained, with every sample we do that iteration, those are learned and those weights are created over there.
Okay, and then the follow-on to that then is, has it been shown that that's the best way to do it? Or even if you know the context of your problem, like I don't have a great example, but if I know that I'm looking for things that have lots of vertical slices through it, for example, I might, as the designer, know that I want it to be looking for that. Does it make sense to apply some of those classical techniques then to precondition the data before you pass it in, or do you just...
We don't use the classical techniques, but we use the same model that we have trained on this model. Instead of starting from initial random weights, we can start from a model that has been trained on ImageNet for classifying, dogs and cats. Now use it to classify, say, between cars and pedestrians in the street. Because the early stages, the features are the same, right? This is what called, you probably have heard or will hear this, transfer learning. So you transfer the learning that you have learned in another application to this new application. You start, instead of starting from random weights, you start from the weights that have been trained for another application and then train from there. So you are halfway there and then you optimize that for your problem.
Okay, thank you.
Thank you.
Okay, I think we have, one more question, maybe 2 if we're quick.
Okay.
Hi, I just had a question about the structure of the networks that you showed before. So you showed, for example, ImageNet, ResNet, VGG. Did they have a strategy in designing these networks, or were they just computationally brute forced, and they just added more layers and determined whether it increased or decreased accuracy?
Adding more layers was one of the ways that had showed that it will increase the accuracy until the time that it reached to a point that it wasn't. That was when the ResNets came. And of course, they are like the reason that VGG used 3x3 stacks together there was a reason for that. Like 3x3 layers of ConvNet is cheaper than 1 7x7, but it basically sees the same area. The receptive field that it sees from the previous layer is the same. So there was some thought into that, but there are also some of them are luck, some of them are really thought into that why we should do these things.
Thank you.
Thanks. Oh, you have a book.
So I had a question about the neural network. How do you build it? So how do you determine how many neurons per layer, how many layers, and what activation functions you would use for those layers?
There is usually, as far as I know, there is no concrete way of calculating those things. It's mostly empirical. And usually, for example, previously we were using sigmoid activation functions. Then we learned that ReLUs are working better in most of the applications, like classification applications. Then everybody switched to that. Somebody discovered leaky ReLU. That's another activation that works better. So people switched to that. And now we have different types of each of these building blocks. We can try. That's why we have a lot of training experiments, and we see which one works better, and that's how it's designed. But there is a lot of empirical side to that.
Okay.
Well, awesome. Well, thanks so
Thank
much.
you.
Thanks again, Mohammed.
Thanks a lot.
It's been great.
Thank you.